Hello everyone, welcome for today's session. So today we will going to talk about the three quantum numbers and the periodic table. So in the last session we have seen the hydrogen atom, the one electron, how it is distributed and how it is placed in the spherical coordinate system. So now we will going to talk about the multi-electron atom, how it is going to be placed in a spherical coordinate system. So now let us switch to our screen. Okay, so here we are talking about the placing of electrons in a multi-electron atom. So if you consider a three-dimensional space like this, because any electron that is present, so that will be in the three-dimensional space or in a spherical coordinate system. So if we consider this is the electron here, then if this is the nucleus or the positively charged nucleus, then the distance between this, we represent the distance between the nucleus here and the electron here with the distance r. And if we mark this position here, then if you mark this, then this angle we call it as the azimuthal angle, and this angle, if you call this as theta, then that will represent the altitude or with respect to this electron. So if we talk about this spherical coordinate system, so we have r, theta and phi. So this we had discussed in the previous tutorial as well. So the representation, the wave function, it is represented as a function of r, theta and psi. So now we talk about the multi-electron. To represent these electrons, we need to have three quantum numbers. So three quantum numbers. So the Schrödinger approach requires the three quantum numbers, that is n, l and ml, to specify the wave function of the electron. So Schrödinger has represented the electron by with the help of n, l and ml, or the quantum numbers, to specify the wave function of electron. So the quantum number is very important because it provides the spatial distribution of an electron. So now let us talk about the first quantum number here. So the first quantum number, we call it as the principal or radial quantum number. Principal or the radial quantum number, and that is represented by n. So the principal or the radial quantum number, it represents the average relative distance of electrons. So if you look at here, if this is the electron here, so the average relative distance from the nucleus. If this point is here at the nucleus, then the distance between this electron and the nucleus, the average distance, that is represented by the principal quantum number. And it also represents the energy level of the electron. So if I write here, so it is one of the three quantum numbers. It is one of the three quantum numbers that tells the average relative distance of an electron from the nucleus, and it also indicates the energy. It also indicates the energy of the electron. So, and that is represented by a variable n, and it has some values, say 1, 2, 3, 4 and so on. It can take any integer value. So now as the value of n increases, it means that if this is the nucleus and if these are represented by the orbits or the shells or the principal shells, so this is with n is equal to 1, this is with n is equal to 2, n is equal to 3, and as the value of n increases, so you see the radial distance of electron and the nucleus increased, and as it increases, it means the bonding is not strong, whereas the electron which is very close to the nucleus has very strong bonding. So the electrons which is far, so it is easy to take out these electrons from the atom. So now let us look into the next quantum number. So the next quantum number is called the orbital or azimuthal quantum number. So the second one is the orbital or azimuthal quantum number, and it is represented by L. So this quantum number represents the shape, it represents the shape of region, or it describes the shape of region of space occupied by an electron. So the orbital or azimuthal quantum number, it indicates or it describes the shape of region of space occupied by an electron. So these are also called as the subshells in the other terminologies. So here the L value range from 0, 1 to any value up to n minus 1. So now for example, if I take the value of n is equal to 0, then L is 0. If n is equal to 1, then L is equal to 0. Sorry, my mistake. N cannot be 0. I'll just erase this. I'll erase this. So if we take n is equal to 1, then L is equal to 0. If n is equal to 2, then L is equal to 0 and maximum 1. And if n is equal to 3, then L is equal to 0, 1 and 2. So this is how we represent. And the region of space occupied by electrons in the same subshells usually have the same shape, but they are oriented differently in the space. So that is the another point which we can remember it. So next, let's talk about the third quantum number. So the third quantum number is the magnetic quantum number. That is represented as ml. So here, this third quantum number, it describes the orientation of the region of space occupied by an electron with respect to an applied magnetic field. So it means it describes the orientation of region of space occupied by an electron with respect to an applied magnetic field, and this is represented by a variable ml, and ml can take any value that is plus or minus L. Now for example, if L is equal to 1, then ML is equal to -1, 0 and 1. So here ML can be considered as the orbitals. So ML represents the orbitals. So a wave function with an allowed combination of n, L, ML quantum numbers, a particular spatial representation. So it means it describes with a combination of n, L and ML quantum numbers, the electron can be specified in a particular spatial distribution. So that is what it means. Now for example, let's take an example here. Or before going to an example, so let us understand. Let's take all the values here. N, I'll take L, and I'll take ML here. So if I consider N is equal to 1, then the value of L is equal to 0, then ML is equal to, then ML can be a value of 0 itself. When N is equal to 2, then L can take two values. One, it is 0, and L can be take a value of say 1. And for L equal to 0, so ML can have a value of only 0, whereas with L equal to 1, then ML can take a value of -1, 0 and 1. So these are what we call the 2s. So basically L representation, that is subshells, can also be represented as S, P, D, F. These are the representation of the subshells. So same thing here. So it means if there is L is equal to 1, it means there is a 1s subshell, and here that is 2s and 2p subshells. So here we have say 1 orbital here, and here we have 3 orbitals. So this is 1 orbital and this is 3 orbitals. And similarly, if I take n is equal to 3, then L can take value L equal to 0, L can take 1, L can take 2. So it means it is 3s, it is 3p, and this is 3d. So here the ML can take a 0, so here ML can take -1, 0, 1, and here ML can take -2, -1, 0, -1 and 2. So it means here it has 1 orbital, here it has 3 orbitals, now here it has 5 orbitals. So hope you got this point. Now if the same thing, if you represent this in a proper table, so just have a proper look here. I'll give you a couple of seconds to have a proper look at this table. So now if you put this in a proper table, and if you represent this with respect to the principal shells, the subshells and orbitals, then we'll get to see all this in a table. Okay, so I'll show you the table here. So now if you see this table here, so now the principal shell n is equal to 1, so the L is equal to 0. It means we have one subshell. Don't get confused with L equal to 0 value and n is with this 1. So it represents this 1 means L is equal to 0. It means we have one subshell. So it means it is 1s. And the ML value, the number of orbitals there, is equal to 1. So when n is equal to 2, so the L value can be two values, that is 0 and 1. So it means we have 2s and 2p subshells, and orbitals is again for here, as you can see that for L equal to 0, ML can take a value 0, and for L equal to 1, ML can take value of -1, 0 and 1. So that is what is shown here. So it means it is 3 orbitals. So now if you can see how many orbitals are here, so here there are 3 orbitals. So this 3 is represented here in the table. And then the number of electrons that it can accommodate. So each subshell can accommodate, or each orbital can accommodate 2 electrons. So here there is a 1 orbital, so it means there are 2 electrons can be accommodated. Here 3 orbitals are there, it means 6 electrons are accommodated. So likewise we can get the subshells and the orbitals. So if you want to see the representation of cells, the shells, subshells and orbitals, so this is the representation, the 3D representation of the orbitals. So here we have the orbitals for 2px, 2py, the different orientations. These are the different orientations. Now this is with respect to y orientation, this is with respect to x, this is respect to z orientation. And this is the third subshell, that is 3D. So here we have the orbitals here. So now the D can have the 5 orbitals, so that you can see here. So these are the different representations. So hope you have understood this. So let us take an example here. So the question is, sorry, how many subshells and orbitals are contained within principal shell, with n equal to 4. So with n equal to 4, how many subshells, how many orbitals are there? So that is the question. So here we will take the same thing here. So if n is equal to 4, so L can be a value of 0, L range from 0, 1, 2, and it goes up to 3. And ML for this is 0, it is 0. This is ML with you say this is 3. I'm not going to write in detail. If you want to write in detail, then it is -1, 0, and 1. And here ML is equal to 5 because it is -2, -1, 0, 1, and 2. So that makes it 5 orbitals. And here ML is equal to 7. So that is -3, -2, -1, 0, 1, 2, 3. So we have this. Now if we total all together here, okay, sorry. So ML can take value of 0, so it means when it takes a value 0, so it means this is equal to 1 here. So if we total all these values, then we will get 16 orbitals. So we have 16 orbitals. Therefore the other way of writing this is, so if you square this principal shell, this number, so we will also get 16, so which is equal to this. So if we square the principal shells, then we will get the total number of orbitals. Okay, so this is a very simple example. So this is about the 3 quantum numbers. So now let us talk about the electron structure of atom. In multi-electron atom, the motion of electron is not only influenced by positively charged nucleus, but also it is influenced by the presence of other electrons. Therefore, to represent the wave function, it is approximated with the help of central field model. I'll not go much in detail of this, so I'll just highlight few points here. So the solution of a Schrodinger equation to represent the wave function of single electron can be characterized, means for a single electron, to represent a single electron we need 3 quantum numbers here that we already seen, that is N, L, and ML. So the total wave function of a system can also be expressed as a product of a 1 electron wave function. Now there is one more important thing that we need to understand here, is that So no two electrons can have uh, so here so what I want to highlight is that the electrons not only orbits around the nucleus but also spins in its own axis. Now if we take some orientation, so if this is the nucleus here and if we take some orbit, so in 1s if we take, so there can accommodate two electrons. It's not only orbiting the nucleus but also it is spinning in its own axis. So according to Pauli's equation, so no two electrons can occupy the same states and they spin in opposite direction. So if it is spinning in a clockwise direction, then other will spin in anti-clockwise direction and have its own axis. And that is represented with the value of say minus half or plus half. And this is represented by another quantum variable that is represented as ms. So now to represent a quantum state, to represent the quantum state of any electron, then we use the four quantum numbers. We use the four quantum numbers, that is now n, ml, ml, and now the new term has come in that is represented as ms. All four together, now it represents the quantum state of an electron, and the ms can take a value of minus half and plus half. So now the electron, one of the electron will spin in anti-clockwise direction and other electron will spin in a clockwise direction, and this spin is parallel or anti-parallel to the orbital momentum. Now the Pauli exclusion principle states, as I told you, no two electrons can occupy the same quantum state. So thus in a multi-electron atom, so no two electrons have an identical set of quantum numbers, and this limits the number of electrons that can go into s, p, d and f levels. So therefore the maximum number of electrons that go in L is represented by 2 into 2L plus 1. So it restricts by this equation. So let me write here the formal Pauli's equation or exclusion principle. So Pauli exclusion principle, it states that in a system no two electron can occupy same quantum state. Thus in a multi-electron atom, no two electron have an identical set of quantum numbers. So this limits the number of electrons that can go to S, P, D and F levels. So therefore the maximum number of electrons for a given L can be defined as 2 of 2L plus 1, and thus S, P, D, F can have a maximum of say 2, 6, 10 and 14 electrons only. Got it? So this is with the Pauli exclusion principle. So now let us talk about a periodic table. So I know you all have studied the periodic table. So, but still, let us have a discussion of periodic table and how it is related to our discussion. We will see that. So I want to show you the periodic table here straight away. Sorry. So now what you see here is the periodic table. So now the periodic table are represented with the different groups, so which represents the same chemical behavior, because these are represented with different groups which has the same number of electrons in the outermost orbit or in the valence orbit. So these are called as the valence electrons. So if you now look into the group 1 here, so group 1 has only if you see that the one electron in the outermost orbit, here also it has one electron in outermost orbit, this also has one electron in outermost orbit, because when you see the hydrogen atom, so it has one electron, that is in 1s. There are 3 electrons here, so 2 goes in 1s and 1 goes in 2s. If you look into here, then 2 goes in 1s, then 2 goes in 2s. So how many are left out? So let's write this. So for Na, which atomic number is equal to 11, then if I write this is nucleus, then this is the 1s, this is 1s, and then for the second, so if I write this is 2s, so this is 2s, so then this is the subshell here, so then remaining 6 goes here, so how many? 2, 4, so 6, 1, 2, 3, 4, 5, and 6 goes. So this is completely filled. Now this is 2p is also filled. Now what we got here is that the one more orbit here, so that we have one electron here, so that you can see from this table. Sorry. Yeah, so that we got in the 3s. So now the one electron here, so that is in 3s. So now all these atoms under the same group represent the same chemical behavior. It exhibits the same chemical behavior, although they have the different atomic number. So that is the one thing that we need to understand from the periodic table. So similarly here, when we go in the horizontally, so we have a periodic table, so we have 7 periods. So this is a period 1, this is period 2, 3, 4, 5, 6 and 7. And if we progress this horizontally, so the atomic number keeps increasing in a linear fashion. So here the atomic number is 1, so then here we have the atomic number 2, and here now the 1s shell is completely filled, that is why it is represented as 1s square. So here the helium is completely filled, and now it is a inert gas. It means it does not react chemically. So that's why it is called as the inert or the noble gases. So these all these the atoms which are in this group, or its outermost orbit is completely filled, and you know, it does not react to any chemical reactions, or it is chemically inert. That is what we call. So now if you look into this, so here we have the 1 electron in the outermost orbit, here 2 electrons in the outermost orbit, here we got 3 electrons, here we got the 4 electrons in the outermost orbit, and so on. It keep on continues, and as it progresses from left to right, we start with one valence electron, with we reach to the 7 valence electrons, and then it is completely filled here in the orbit, and we reach the inert level. But as we look into this here, there is a special case for this K atom for the potassium with atomic number 19, and Ca for calcium with atomic number 20. So now if you look into this case, the number of electron distribution. So after 3p6, when 3p is completely filled with 6 electrons, so the next orbit or the next subshell supposed to be 3d, but rather than going to 3d, it goes to 4s. So the concept is that, so let me take that, the potassium, so here the K with 19. So for K equal to 19, if I write the electron distribution, then it is 1s squared, then we have 2s squared, then 2p6. So how many electrons we got? So 6 plus 2, 10. Then we have 3s squared, 3p6, and now we have left out with 1 electron. It's supposed to go to 3d1, but it does not go to 3d, rather than it goes to 4s, and it takes 1 electron in the 4s orbit. The reason for that is it says that n plus L, if it results in the lower energy level than 3D, then we go for n plus L. So if I state this formally, so it means the electron with Z equal to 19 would normally be expected to go to 3D subshell, since one expects this to be in the higher energy level next to 3p level. However, it has shown that in many electrons the energy is lowest for the state for which n plus L is lower. So now if we take n plus L, so what is the value of n here? So here n is equal to 1, here n is equal to 2, here n is equal to 3, here n is equal to 4. With this n equal to 4, what are the value of L it can take? So L can take, this is 0, L can take 1, L can take 2, L can take 3. So now with L equal to 0, so now if we add this 4 plus 0, so what do we get here is 4 itself. So it means it is relatively at the lower energy level. So whereas in this case, what is the value of L here? So L takes for this, so here L is 0, here L is 1, here L is 2. So if we add, so then it will become 3 plus 2 is equal to 5. So it means this is at the higher energy level when compared to this. So rather than electron going into 3d1, it goes to 4s1, and it occupies this electron. So likewise, even for calcium, also the same thing with atomic number 20. So even with the atomic number 20 with n equal to 4, it goes to 4s rather than rather than it goes into with n equal to 3, rather than going into 3d. Why? Because again here L is equal to 0, so n plus L. So here so it becomes 5 in this case, but still both are is equal to 5. So though both are equal to 5 in this case, so what happens is that L is equal to 1. It still takes the 4s orbit. Got it? So that is why then after that, if you look into the other distributions, when it comes to 21, then it goes to 3D and then it goes to 4s. So the another formal way of writing this is to understand. So you can think like this. So it is 1s, 2s, then 2p, then 3s, 3p, 3d, then 4s, 4p, 4d, then 5s, and 5p. So if I put the circle like this for all, then how does it progress? The simplest way to remember is it goes like this. Sorry. something like this, and it comes here and goes here, then it will take these values and it comes here and it take these values and it comes here and it will take these values. So like this you can remember. So hope this is, I think it is not clear. Let me show you which is already there. So like this. So first it will take 1s, then 2s, 2p, then 3s, and after 3s it comes to 3p, then after 3p it comes to 4s. So this is the easiest way to remember. Then it goes to 3d and then 4p and so on, it continues. So this is the distribution which is represented here with respect to 4s, then it comes to 3d back, and then again 4p and so on, it continues. So before winding, I want to highlight here, so the elements in the group 1 here, so group 1, 2 and 3, so these electrons, if it loses 1 or 2, 3 electrons loses, then it becomes an inert gas, and this we call it as the electronically positive ions. So this will become a positively charged ion, so we call it as electropositive ions. So likewise the group 7, 5 and 6, if it loses, if it gains 1, 2, 3 electrons, then it becomes a negative ion, so we call it as electronegative. And whereas the group 4 is our interest. So now if you look into group 4 is where our semiconductor items exist. That is the silicon, germanium, all these, which has the 4 electrons in the outermost orbit, and these acts as the electronegative and electropositive elements. So that's it for today's discussion. So thank you.